All right, so let's get into some fun math here. All right, so we're trying to model, where cities come from, and we have this idea that location really matters. So what we're going to do is we're going to say this S, which you want to think about it like the city's population. Now, technically, what it is the share of the population located in the city. So if like 20% of the population live in that city, it's 20%. It's probably easier just to think of it like this is like how large the city is. So the bigger the city, the higher this number is going to be. That's going to be determined by time invariant characteristic of the city. Whatever is special about that city, we're going to call this characteristic. Denote it with the I. I is the city. So each little I is a city. And then T, the subscript T is time. So we're going to say, look, the population share of city I in time T is a function of its underlying characteristic. So if this is a big number, it has larger. So if this is good, if it has good characteristics, this is a larger number. And then this is a random variable. Okay, so this thing is just a random variable. Sometimes you have a good year where people want to come to your city. Sometimes you have a bad year where people don't want to come to your city. Okay, that's what this represents. Now, what we want to know is how correlated is this shock over time? So you get this shock to your population, this random variable. Is your shock in the next period related to that shock or not? So if you get a bad shock, basically if your city gets knocked off its path, if your city gets a bad shock, does that bad shock persist? Do you just keep getting bad shocks? Once people start leaving, do they just keep leaving? That's what this equation represents. So what this says is, okay, here's your shock. The shock you get in the next period is a function of your old shock plus another random variable. Now this is a true random variable with a mean 0. This number could go from 0 to 1. So if it's 0, notice that this is 0, and your shock is totally random. This is a totally random variable. Now, if this is 0, this is a totally random variable. So your shock doesn't persist if this variable rho, this is like a fancy, this is the Greek letter rho, I believe it's rho. It looks like a P, but it's rho. We always use Greek letters. I don't know why. That's just what we do. We use Greek letters to be fancy. So if this is 0, the shock doesn't persist. It's just completely random what shock you get each period for your city. And the overwhelming important variable is this guy, the characteristics of your city. Okay. So if it's 0, doesn't persist. Now, if it's 1, then basically it fully persists. Then, you're going to get some randomness here, but your shock in the next period is going to be really dependent on what it was last period. So once you get a bad shock, you just keep getting bad negative shocks. Once you get a good shock, you keep on getting good shocks. So we have basically two different worlds. The location fundamentals world would say this is 0. What really matters is the underlying characteristics. The non-location fundamental world would say this is 1, or close to 1, in that, sure, the location matters initially, but what matters after that is whatever random shocks you get, whatever happens in the city, that's going to override the characteristics. So the cities that get the good shocks will keep getting the good shocks. Okay, so let's not worry about this equation yet. Let's go to the next page. Okay. And this is going to clarify a little bit of our thinking here. So let's write our let's see if I can write this like this. I T plus 1. Okay. Now this is going to equal the characteristics I plus the random shock, which I'm going to write as E. Don't have I and then T plus 1. Okay. So I'm just rewriting. Here's what I'm rewriting. I'm rewriting this equation. Okay. This equation right here, but in the next period. I'm moving it forward to T plus 1 period. Okay. So this is your share in the next period. is a function of your characteristic and this shock. Okay. All right. So then what I'm after is these formulas right here. So what I'm trying to show you is how did I arrive at these formulas? Okay. So then I have my E, my shock from the next period. Let me write it like this, maybe a little clearer. ET plus 1 is going to equal rho times E underscore I T plus this guy, which is V, I believe that's omega, and then T plus 1. Okay. All right. Let's put parenthesis on there. Okay. So this is my population in the next period. It's a function of my characteristic plus this random shock, where this random shock is a function of last period's shock plus a random variable. Now, if rho is 0, if this thing is 0, okay, then this is 0. This just goes away. And this thing just equals this thing. So this random shock just equals that. So if rho 0, what I have is my population in the next period is a function of my underlying characteristic and a pure random variable. Okay. All right. Let's see how we got this equation right here. So we're going to have our share in the next period is going to be equal to the characteristic. Okay. Now, what is this? This, as we know, is rho times this guy, this random variable, okay, plus V I T plus 1. Okay. All right. Now, this is 1. Now we're saying this is 1. So we can rewrite this as this thing, T plus 1, okay, is equal to the characteristic I. Now this is 1, so I could rewrite this as this guy. Okay, plus V I T plus 1. Okay. Now this thing right here, characteristic I, characteristic of the city plus this random variable, that is just our definition of this thing, the previous period's population share. So if I could take that out and substitute it for this, and there I'd be left with this equation. So here are our two key equations. All right. If rho is 1, what's going to happen is my population is going to be dependent on last period's population plus just a random variable. If rho is 0, then my population is going to be dependent on the underlying characteristic of the city, not last period's population. It's going to be really dependent on whatever this underlying characteristic is. So basically this says shocks matter, that shocks will persist. If you have a low population, you'll continue to have a low population. This says, no, what matters is the underlying characteristics. That is what determines your city's population ultimately, is the underlying characteristics. So we have two different worlds here, where rho is 0 and underlying characteristic really matters, and where rho is 1, where shocks persist. Okay, a lot of math, but very, very clever, very good model, because what we're after, we're trying to estimate these things. We're trying to figure out what is going on. This gives us a framework on how to look at the data. We're gonna have a bunch of data on these Japanese cities' size, and we're gonna need to figure out, do the shocks persist or not? Does it really matter when the cities that are bombed heavily, is that what's important, or is it the underlying characteristics? This gives us a framework to think about this. This gives us a framework to take to the data, use our econometrics, and estimate something. What we're going to try to estimate is this. If this is 1, if rho is 1, that tells us that the shocks really matter. The shocks persist. If rho is 0, that tells us, nope, underlying characteristics are what's important. Okay, so how are we going to do this? All right. what we are going to do is we're going to take this equation. Where did we get this equation? We wrote down SIT plus 1, imagine written above here, subtracted, you get this thing, okay? Then what you do, you take 2, take this guy, put that in right here, do some algebra. I'm not going to do the algebra, but you do some algebra and just trust me, you will arrive at this equation right here. It doesn't look like I've made my life any easier. Just wait, just wait, just wait, just wait. So we just do a little bit of algebra. Again, we're going to rewrite this as SIT plus 1, write that out, subtract SIT plus 1 minus SIT. We get this equation, substitute this into here, do some more algebra, we get this. Okay. All right, now what we can do is we can rewrite this with real variables. SIT plus 1, that is like your population in 1960. The next period that we have good data for is 1960. So we're going to take population in 1960 minus the population in 1947, which is going to be after the bad shock. Okay, after the bombing shock. Then, so we'll have rho minus 1 times this random variable, whatever this random variable is, VI 47. This is the random shock. So this is how hard did you get hit during the war? All right. So that's what this one's going to be. Basically, it's going to say, you know, how hard VIT here for EIT for this imagine an equation written out for EIT. That is going to be determined by this random variable. And so these cities that got hit really bad in the war, this is going to be a big old negative number, big negative shock. Okay. So we have that. So we know the populations between these two eras. We know how bad the shock was from the war. This is just going to be noise, okay? This is a random variable in 1960. That's totally random. We are going to assume rho is either 0 or 1. So if rho is 1, 1 minus 1, 0. So this is 0. If rho is 0, 0 times this is 0. So this is going to be 0. We're going to assume it's either 0 or 1. So this is 0. You can get rid of this. This is a random variable. Now we can use regression, okay? Now we can use a regression to estimate what this is. We can regress the change in population on the negative shock to get an estimate for this guy, which will then tell us what rho is. If you're not familiar with regressions, basically they fit a line to data. And so if we have this data and this data, we can basically estimate the line of best fit, and this will be the slope of that line. But basically, we can use statistical techniques to estimate this guy. All right. And if we do that, we get this. Okay. All right. So we get this. We basically get -1. All right. So we get -1. If this is -1, that means rho is 0. Okay. So when we estimate this coefficient right here using the data, well, not when we, but when these authors did it, they got -1, which tells us rho is 0. So for Japan in this time period, what this paper showed was that rho was 0. The fundamental characteristics of cities is what mattered. So what they saw was cities bounced back. Those cities that were bombed the most bounced back the most, which would suggest it's the underlying characteristic of the city that's mattered. Cities that are situated in good areas that are beneficial for trade or close to resources bounce back to their former populations. Those negative shocks did not persist. Okay, and this graph will kind of illustrate this. So this is how fast did you grow from 1947 to 1946, and this is how bad were you bombed. So the growth rate here is negative. So most of these are negative. So these big circles are, this is each city. The circle is the size of the city. So these cities over here, this is probably Tokyo, Tokyo and Osaka, if I had to guess. So these cities over here were the ones that got bombed the most. They had negative growth rates from 1940 to 1947. And lo and behold, those are the ones that grew the most from 47 to 46. They essentially had the negative shock, bounced all the way back. And so you can see basically this relationship, that the harder the city was hit, the more it bounced back, which tells you location fundamentals really matter. And we can see this most drastically with Hiroshima and Nagasaki, where these cities were decimated. Here's their population with the after the atom bomb, and then you can see that basically they return back to their pre-war growth path. That there's something fundamental about these cities that made them important, and even after the bombing, they return back to their pre-war paths. Okay, let's stop there. Let all that math sink in. We'll pick it up in a second.